Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 17 of the course Stochastic Hydrology. If you recall, in the last lecture we discussed the ARIMA models and specifically how the AR and MA components of the model behave. For example, we considered AR1 model, formulated a theoretical AR1 model and saw how the correlogram of the theoretical AR1 model behaves and how the spectrum behaves and how the PAC function behaves, that is the partial autocorrelation function behaves. And then we also looked at two examples of AR2 models, and similarly for MA1 process we saw how the autocorrelation, partial autocorrelation function and the spectral density function behave. So, we essentially identify the number of AR terms and the number of MA terms in a ARIMA model by looking at the PAC function as well as the correlogram. But as I said in the last lecture, when you have both AR and MA terms in the model and they are slightly of higher order, let us say that you are talking about ARIMA 4, 5, ARIMA 4, 2, 4, 1, these kind of models where the number of AR terms is quite large and the MA terms are also reasonably large in number, then identification becomes quite difficult, and therefore, what we do is we formulate candidate models, several of candidate models, and then for the candidate models we examine, we estimate the parameters and then examine whether the model is valid or not. Then we also examined in the last lecture the procedure for parameter estimation. As I mentioned, there are several algorithms available for parameter estimation, and we introduced the MATLAB function Rmax, which can be readily used, and the parameters for any given ARIMA type of model can be estimated. We towards the end of the lecture, we examined the maximum likelihood criterion for selection of the models. The specific problem is that we have a number of candidate models, we have estimated all the parameters for the models based on the data. Please do not lose sight of the hydrologic aspects of this. We have observed data, for example, the stream flow at a particular location, and then on these observed data we are doing all of this exercise, so that we can fit a model for the time series that has been observed. So, once we formulate the candidate models and estimate the parameters for each of these models, then we have to choose which among these candidate models is best suited for the observed data. This we do by two methods, as I mentioned in the last lecture. One is the maximum likelihood criterion, which we use for when your application is for long term simulation of the data, then we use the maximum likelihood criterion. What we did in that, we defined a likelihood function, log likelihood function to be precise, and estimate the log likelihood function value for each of the models. So, each of the model will have one log likelihood value, then pick up that particular model which results in the maximum value of the log likelihood function value. Now, we will go to the second part of the applications of the model, where the models are meant not so much for a long term synthetic data generation, but for one time real time forecasting models, that means one time step ahead forecasting models. Like I mentioned, these applications will be for example, monthly forecasting of the stream flows, which may be useful for your real time operation of the reservoirs, where you are operating the reservoir for irrigation, hydropower, etc., depending on the storage level and depending on the forecast of the flows, you would like to operate the gates. This also becomes important when we are looking at smaller time periods like 10-day time periods for real time irrigation scheduling and so on. When we look at the applications, these points will be clear, but essentially we use the time series models to develop forecasting, develop forecasts for the reservoir inflows, evapotranspiration, rainfall and so on and so forth. So, when our applications are for short term forecasting, then the maximum likelihood criterion is not the criterion that we use. We must then go for the minimum mean square error criterion. Now, that is what we will discuss in the lecture today, how we develop the minimum mean square error values for the models and then pick the best model that gives the minimum mean square error. So, the minimum mean square error criterion or the MSC in short, which is also called as a prediction approach. What we do in this is that let us say you have 50 years of data, monthly stream flow data, then we use the first 20-25 years of data to formulate the mean square error. Let us look at this sketch here. Let us say that your time is on this scale and you have n values of the time series. We use the first n by 2 values typically for developing the model, and then the remaining n by 2 we use for calculating the MSE. So, we calculate the mean square error with the remaining n by 2 values. What do I mean by that? Let us say that you have fit a AR1 type of model for using this particular data. When I say you have fit the model, it means that the parameters have been estimated for this particular model. How do I write this? We write this as x t is equal to, in our notation, phi 1 x t minus 1 plus epsilon t. Now, this is the model that we have written and we have estimated the parameter phi 1 using one of the algorithms. Now, when we want to use this model for forecasting, what does the forecast mean? Remember that this is a noise term here or a residual term which has a 0 mean and they are all uncorrelated, the epsilon t are all uncorrelated. When we want to use this particular model for forecasting purpose, the forecast is the expected value for the next time period. Let us say that you are standing in time period t and you want to forecast for time period t plus 1. So, you are here now and you know the information that is available up to this particular point and you want to forecast for x t plus 1. Let us say that I write x t plus 1 is equal to phi 1 x t plus epsilon t plus 1. I am writing it for t plus 1 now. Then for forecasting, whenever we say we want to forecast this using this particular model, what is it that we are doing? We want to get the expected value of x t plus 1 given the entire history up to time period t. That is the problem. So, we want to see what is the expected value of the flow for time period t plus 1 given the value until x t. Now, to do this, I will take the expected value of x t plus 1 now. Let us say I write x expected value of x t plus 1. So, I am taking the expected value of this particular expression is equal to phi 1 into expected value of x t plus expected value of epsilon t plus 1. Now, this is the forecast and we then generally denote the forecast by putting a cap on that particular variable. So, x t plus 1 cap, which is the forecast for the time period t plus 1, is equal to phi 1 expected value of x t plus expected value of epsilon t plus 1. So, I will write expect the forecast x cap t plus 1 is equal to phi 1 expected value of x p x t, I will write keep it as it is, plus what is this? This has the mean of 0. The epsilon t, remember, is a sequence which has a mean of 0. So, when you take the expected value of epsilon t or epsilon t plus 1, that is 0 here. So, this is simply phi 1 expected value of x t. Similarly, you can look at any models. Let us say that you want to take ARIMA 1 model here and then use it for forecasting. So, ARIMA 1 model, we write it as x t plus 1. Let us say again we look at 2 time periods, 2 adjacent time periods, time t plus 1. You are here now and you want to forecast for the next time period. To keep the relevance with hydrology, let us say that you are standing in the month of June and you have the flow information up to the month of June and you would like to forecast what is likely to happen to the next month, that is the flow during the next month, if you are looking at the forecast for flows. So, we will write this as x t plus 1 cap is equal to expected value of okay, I am sorry, I will write first the model here. So, ARIMA 1 model we will write first. We write ARIMA 1 model as for x t plus 1 is equal to, I have one AR term. So, I will write this as phi 1 into x t. I have one MA term. So, I will write this as theta 1 into E t plus E t plus 1, because I am writing for time period t plus 1. Now, you would like to forecast, use this model for forecasting. As I said, what do we mean by forecast? Forecast is the expected value of the particular variable, stream flow in this particular case, for example, for the next time period t plus 1. So, we take the expected value of x t plus 1. I will write that as expected value of x t plus 1 is equal to phi 1 expected value of x t plus theta 1 expected value of E t plus E t plus 1. Remember here, when you are writing a ARIMA 1 model, the E t term here is the residual arising out of the application of this model in the time period t. So, when you write this expected value of E t in this particular term, the E t value is a constant, it is not the expected value of t plus 1 that becomes 0. For example, we may be talking about expected value of 5 units and therefore, this becomes E t itself. So, I will write this as x t plus 1 cap is equal to phi 1 expected value of x t plus theta 1 E t plus expected value of x t plus 1 E t plus 1, which is 0. What is the difference here? What I did is that this is the actual value of residual that resulted from this. So, this is the actual value of residual that results from applying this particular model for the time period t. So, there was a residual, there was the actual value that was available and then the forecasted value was available. So, the actual value minus forecasted value gave me this E t value and therefore, when I take the expected value it becomes E t itself. So, I will write this as phi 1 expected value of x t plus theta 1 E t and this becomes 0 because these are all noise terms. And therefore, you write the forecasted value for time period t plus 1. essentially then we are getting the forecasted values and applying for the first n by 2 terms that you have. As I mentioned, you have n by 2 here, number of values, and you have another n by 2 number of values. So, what we did? We have developed the model using this n by 2 number of values. This is the for model development. By model development, I mean we used all of these values to obtain the parameters of the candidate models. We had, let us say, for the forecasting we had the models AR1, AR2, ARIMA 11, ARIMA 12 and so on. As I mentioned in the last class, when we are talking about the forecasting models, typically the lower order models in terms of the number of parameters will suffice. In fact, when we see in the applications most often the AR1 or AR2 model themselves will be sufficient for one time step ahead forecasting, especially when we are talking about smoothened processes like monthly stream flows, seasonal flows and so on. So, we choose the candidate models which may be different from the candidate models that you would have chosen for long term synthetic generation of the data. We chose that and then developed the model using the first n by 2 values. Let us say if you had 50 years of values, you would have 50 into 12, that is 600 values is the data. This is number of years and this is number of months. So, you would have 600 values. So, use the first 25 years data which is n by 2 to develop the model and then calculate the errors of using this model on one time step ahead forecasting for the remaining data, remaining part. What do I mean by that? Let us say that you chose your AR1 model. So, in the AR1 model you would have written your expected value of x t is equal to phi 1 into expected value of x, that is forecast for time period t plus 1, you would have written as phi 1 into x t bar or is equal to phi 1 expected value of x t. So, this phi 1 you would estimate based on the first n by 2 values of the data and then start applying this. When you start applying this, let us say that you are now applying for the remaining n by 2 values and this is one time step ahead forecast. So, given x t now, you had this x t value known, you want to apply this. So, I will get x t plus 1 cap, this is known, x t is known. Typically, let us say you are standing at the end of one month, June month, the flow during the month of June is known, you want to forecast the flow during the month July. Then we apply this, phi 1 is known, phi 1 is estimated already. So, we apply this as x bar t plus 1 is equal to phi 1 into expected value of x t, that becomes x t itself because it is known. So, this you get x bar t plus 1, but because you have the data already for this n by 2, this data is available. What we do? This is the forecasted value and x t is the actual known value of the flow. Let us say that you have x t available with you. So, I will take the error of forecast. So, what will be the error of forecast? X t plus 1 is your known data, I will say this is known data and x t plus 1 cap is your forecasted value. let us say known data value. So, the error I will write for the time period t plus 1 is equal to x t plus 1 minus x cap t plus 1. This is what is forecasted from the model. So, like this I get error. Now, we are writing for the remaining n by 2 time periods. So, next time when I go, let us say that I want to write for x t plus 2 now. So, I finished my forecasting problem for t plus 1. So, I come to t plus 2. When I am writing for the next time period, we use the actual value that is known x t plus 1 to get for x t plus 2, the forecast, not the forecasted value, remember, because this data is already available and the question that we are asking is standing at this point, knowing the value up to this point, what is my forecast for the next time period. So, x t plus 2 I will write this as phi 1 x t plus 1, the expected value of x t plus 1, which becomes x t plus 1 itself, because this is known here, plus expected value of the error term, which is 0. So, I will simply get x t plus 1 based on this, x t plus 2 based on this. Then again calculate the error corresponding to x t plus 2, because the x t plus 2 forecast, because you know the x t plus 2 value itself, and therefore, you get errors of t plus 1, t plus 2, errors corresponding to t plus 1, t plus 2 and so on. So, you formulate the error sequence. Using the error sequence, then you can get the mean square error. So, this is the procedure that we use to obtain the errors of forecast. So, the same thing is summarized here. Using a portion of available data, which is typically n by 2, estimate the parameters of different candidate models. Use this forecasted models so developed, all the candidate models one by one, to get the series of forecasts one time step ahead by using the candidate models. And corresponding to each of these forecasts, you know the error term, get the mean square error, and then pick up that particular model which results in the minimum mean square error. It is written more formally like this. So, one time step ahead forecast for ARIMA PQ model now can be written as x bar t plus 1, you have p of AR terms x j x t minus j, plus you have q of moving average terms j is equal to 1 to q phi j E t minus j. The noise term has mean 0, therefore, it when you take the expected value, it vanishes. And then the error for one time step ahead forecast is E t plus 1 is equal to x t plus 1, which is the known value minus the forecasted value. Once you know E t plus 1, then you get the mean square error. Mean square error is because you have used n by 2 number of values, you sum all these errors, the squares of the errors, and then divide by n by 2, you get the mean square error, and choose that particular model among the candidate models, among the number of candidate models, to pick the particular model which results in the minimum mean square error. All right. Now, what did we do? Whether it is for long term simulation of the data or it is for short term one time step ahead forecasting, we use the models, ARIMA models, and integration we used for differencing. So, typically we difference the series first and then apply the ARIMA models. So, whenever I say ARIMA models, the integration is applied, implied, that is the differencing is already done, and on that we are applying the ARIMA models. So, in either case, whether it is being used for long term sequence synthetic generation or for short term duration of the data, we use part of the data for calibration and parameter estimation. The remaining part we are using it for validation type. Let us say you are using it for long term simulation, and it is of ARIMA type of model, ARIMA 1 1 or ARIMA 2 1 etc. So, there is also a MA model available, MA term that is available. Then what we do, that we apply it for x t plus 1, get x t plus 1. You already have a known x t plus 1. So, the residue term E t plus 1 is got from the available data minus the model data. Same principle as we did for forecasting. So, you generate corresponding to this term the residual series E t series. Similarly, if you are using it for the forecast, the error of the forecast that we just obtained there, that error term becomes a residual series. So, for the test data you have generated E t plus 1, E t plus 2, E t plus 3 etc. up to all the values, all the remaining values. So, you have essentially the residual series available with you after you apply the model. Now, for the validation of the model, we test this residual series that you so obtained. That means, you applied the model for the remaining n by 2 values or whatever number of values that you have chosen for validation. Corresponding to each of the term, you obtain either the residual or the forecast error. So, E t sequence is known. On this E t sequence, now we carry out all the tests. What are the tests? The tests, if you recall, when we formulated these models, we wrote the residual or the noise term E t and said that the noise term should have a 0 mean. That is the first assumption of the model. Next, that it should be devoid of periodicities and it should be uncorrelated. So, we do 3 primary tests, primarily 3 tests we do. One is to test the series that we have generated, namely E t series. This series has a 0 mean and that the series is devoid of any periodicities and also that the series is uncorrelated. So, we perform the test. So, examine whether these assumptions that we have made, that is the residual series has a 0 mean, no significant periodicities are present in the residual series and that the residual series is uncorrelated. How do we formulate the residual series? As I said, this is E t is the residual is equal to x t, which is the known data, minus you have this term corresponding to the simulated data from the model. So, this is phi j x t minus j plus theta j E t minus j. So, this is how you calculate the E t term. So, you have the sequence of E t's now. On this sequence of E t, we do the following validation test. One is significance of the residual mean, that what is it that we want to test here, that the mean of the residues that we so obtain have a mean of is 0, the mean is 0, but obviously it will not be exactly equal to 0. Therefore, the mean should be not far away from 0. So, we say that the mean is not significantly different from 0, that is the test that we make in this. Similarly, significance of periodicities, you may still have periodicities present in the data when you do the spectral analysis, the spikes may still appear, but the periodicities that you identify on the residual series when you carry out the spectral analysis must be insignificant, all of them must be insignificant. Now, in this we do the cumulative periodogram test for this, and then we also do the white noise test to make sure that the series is uncorrelated. In the white noise test, we will carry out Whittle's test and portmanteau test. Typically, in most of these tests, we formulate an appropriate statistic and then knowing the knowing that statistic follows either a f distribution or t distribution corresponding to critical values of f and t, we decide whether the particular series that we have passes the test or not. Exception to that is the cumulative periodogram test, where all the periodicities are tested at once in one go. We will see the details of this now. So, for the significance of residual mean, it examines the validity of the assumption that the error series E t has a 0 mean, or the mean of the E t is not significantly different from 0. So, we define, I follow Kashyap and Rao's book here, this is a book, reference is given here. We form a statistic eta E as n to the power half E bar by rho cap 1 by 2. Remember, rho cap here is not correlation, but it is a residual variance. So, you had the residual series, and the residual series you have calculated the mean, that is residual series is E t, this is given now, and then E bar is associated with this E t, and rho cap is the variance of this E t, and n is the number of values, n is the data sample length. So, you get n of E. Once you get eta of E, I am sorry, eta of E, eta of E is known to be approximately distributed as T alpha n minus 1, where alpha is the significance level. For example, you pick 95% or 99%, and then you get the T alpha comma n minus 1, n is the number of data. If the value of eta E that you so compute using this is less than the critical T value, this is the critical T value corresponding to the level of significance that you choose. If this value is less, then the mean of the residual series is not significantly different from 0, and then we say that the series passes the test. It is pretty simple, as you can see, the entire series is considered first, residual series E t, and then you formulate for the entire series, you formulate one value of eta E, which is a statistic, and then look at, compare the eta E you so compute with the T distribution of a specified alpha value, and then look at whether this eta E value that you have computed is in fact less than the critical T value, and then we say the series passes. So, that was the test for significance of the mean. Now, the mean may be 0, but still you may have periodicities present in the residuals, and the residual series that you obtain from the model should be devoid of any periodicities. Therefore, we look for significance of the periodicities, and in fact, the residual series should not have any significant periodicities present in the data. Now, I will discuss two tests, both of the tests are valid, but one is slightly superior to the other as we presently state. So, the first test, again you formulate a statistic eta E is equal to gamma k square into n minus 2 by 4 rho 1 cap. Remember, we are doing the test for periodicities here. We pick one periodicity at a time. So, the test is conducted for different periodicities. Let us say that the error series that you get has some periodicities present. Let us say that this is a residual series, and then you see that there are certain periodicities here like this. So, we pick the periodicity corresponding to this particular omega value first, and then carry out this test. So, the k that I am mentioning here corresponds to the particular periodicity that you want to test, one at a time we are testing. So, corresponding to that particular value of k, you calculate gamma k square, and rho 1 again is the variance of the residual series. So, we know rho 1 cap, and gamma k will compute simply alpha k square plus beta k square as we did in our spectral analysis. N is the total number of values that you have. So, gamma k square is equal to alpha k square plus beta k square for the particular value of k. As I mentioned here, gamma k corresponds to the periodicity being tested. So, in this case we may be testing for this particular value, and the omega k that we do in our spectral analysis, let us say that this is omega k we are writing, and this is I k with our notations. We pick up that particular omega k, and then for that particular k we compute gamma k. Then rho 1 cap, I am sorry, I mentioned this as the variance. Rho 1 cap is computed based on your E t. This is actually minus alpha 1 cos omega k t. This is corresponding to that particular k value omega k minus beta cap sin omega k t whole square, and alpha k we know 2 by n. This is from our spectral analysis. So, alpha k and beta k you get directly from the spectral analysis. So, rho 1 cap is obtained from this for that particular periodicity which we are examining now. I again repeat, this test tests one periodicity at a time. So, we pick that particular omega k, and then corresponding to that k we calculate gamma k, and similarly rho 1 cap is known. See here all these values are known, alpha k is known, alpha cap is alpha k actually, and then you have the beta k value which is also known. For completeness sake, let me make this correction, this is alpha k cap and this is beta k cap for that particular k, and then you calculate rho 1 cap. So, rho 1 cap is known in this statistic, gamma k is known, rho 1 cap is known, and therefore, you can compute the statistic. Now, the periodicity for which the test is being carried out is 2 pi by omega k. Let us say you obtain a 12 months periodicity even in the residuals, then the corresponding value of omega k is 2 pi by that particular periodicity. So, the statistic eta e is approximately distributed as f 2 n minus 1 n minus 2, where alpha is the significance level. The f distribution tables, if you look up in any standard textbook, they will give for each of these significance level the number of degrees of freedom and for the number of values. So, let us say you choose f alpha as f 0.95 or alpha as 0.95, 95% significance. Corresponding to 95% significance, you compute these. In fact, this is just the same test that we did in our spectral analysis to identify the significance of periodicities. And then you check the statistic, that value of the statistic that you have calculated, eta of e. If this is less than f alpha 2 n minus 2, then the periodicity is not significant. Let us say that your spectral analysis like this shows up 2 or 3 different periodicities. First you test for this periodicity. If this is not significant, then naturally these periodicities may not be significant if they are all in decreasing order like this. However, you may have a case where this may be significant. If one of them is significant, then you have to test for the next periodicity also. So, you keep testing for the periodicities until you are satisfied that all the periodicities that are thrown up by the spectral analysis of the residual series are all insignificant. Then the series passes the test. Even if one periodicity is significant, then the particular model does not pass the test. Now, for the significance of periodicities, we also have another test which is called as the cumulative periodogram test or the Bartlett's test. The advantage of this Bartlett's test is that unlike the previous test that I just explained, this test examines all the periodicities at one time rather than going by one periodicity to another, and therefore, this is computationally convenient. So, the test is more convenient and is preferred because of its ability to test all the periodicities at a time. So, essentially what we do in this test is that we form a cumulative periodogram as follows. We define gamma k for k is equal to 1 to n by 2. As I mentioned, this is a validation test. So, this is validation period. For the n by 2 values, you calculate gamma k square. Corresponding to each of the k, you know omega k from your spectral density, you would have computed this, and E t is that particular value of the residual series, and you are summing over t is equal to 1 to n, t is equal to 1 to n, and therefore, all the terms are known here. So, for k is equal to 1 you get gamma k, k is equal to 2 you get gamma k, and so on. So, like this for k is equal to n by 2 you have gamma k square. Then you determine g k as j is equal to 1 to k summation gamma j square. So, from 1 to k you are adding up gamma j square. So, g 1 you have one term, g 2 you have two terms, 3 you have 3 terms, and so on. Like this you calculate summation of this divided by over the entire period, k is equal to 1 to n by 2 gamma k square. So, the plot of g k versus k is called as the cumulative periodogram. So, you know how to compute g k, all values are known here, therefore, you can calculate gamma k. Once you know gamma k, you sum up to k and then get g k by normalizing with respect to the entire sum here. And because of this nature, g k varies from 0 to 1, the maximum value it can take is 1. Then we plot k on the x axis and g k on the y axis. Now, I will explain this with respect to this figure. So, you computed g k and you have the k values. So, this is the plot, this black line you are seeing is the plot of g k versus k for the residual series. Now, on this we have used n by 2 values and the maximum value of g k is 1. So, draw a line between 0 and n by 2 comma 1. This corresponds to a frequency of 0.5. So, 0.5 comma 1 on the frequency diagram. So, draw a line, this is the red line here. On this line, on either side of this red line, you draw the confidence bands. The confidence band is gamma, that is lambda divided by root of n by 2. So, this is lambda by root n by 2 on either side of the line so drawn. So, like this you get a band now, this is a band. If your cumulative periodogram that you have drawn, any part of that goes above or below, goes beyond the bound that you have drawn, then the series does not pass the test. In fact, it means that corresponding to that particular, let us say that it was beyond this particular band at a particular k value, the periodicity corresponding to that particular k value in the residual series is significant. If the periodogram completely lies within this band, then it is not significant. So, this is how we examine the significance of the periodicities. So, let me summarize that. So, you draw first the cumulative periodogram by considering g k, by constructing g k for each of the k values. You have n by 2 values and therefore, you construct g k versus k for n by 2 values, and then on the cumulative periodogram 2 confidence limits given by lambda by root n by 2 are drawn on either side of the line joining 0 0 and n by 2 1, n by 2 1. What is 1? 1 is the maximum value of this and n by 2 corresponds to your k max, there is a maximum lag. In fact, this corresponds to a frequency of 0.5. Then what is this lambda value? The value of lambda for 95% confidence limit is 1.35 and for 99% confidence limit is 1.65. In fact, this test also I have taken it from Kashyap and Rao. So, you can refer to Kashyap and Rao, these are the values prescribed for this. So, you know how to draw the bonds now, you know you have drawn the cumulative periodogram, you also know how to draw the bonds. Now, if all the GK values lie within the significance band, there is no significant periodicity present in the series, which means that the series passes the test. If a particular value of GK lies outside the significance band, the periodicity corresponding to that value of GK is significant, and therefore, the series does not pass the test. So, this is how we calculate we carry out the Bartlett's test or the cumulative periodogram test. In most of the cases, if the models are acceptable, the residual series typically gives typically lies well within the bonds that you have drawn. It hardly comes very close to these bonds. In fact, when I discuss the case studies, it will be clear. However, just for your curiosity, what you can do is you draw the cumulative periodogram also for the original data. Then you will see that there are several periodicities which are lying way above and below this particular band, either on this side or on this side. So, indicating that the periodicities are significant. Now, we will see the white noise test. So, what we did is for the periodicities we have now two tests, and typically we prefer the Bartlett's test because of its ability to test all the periodicities in one go, and also computationally it is very simple. That means, you simply calculate GK much like your correlogram, you formulate the periodogram. With respect to lag k, you calculate GK values and plot this, and immediately this significance comes up. Whereas, in the first test that we had, we formulated a statistic corresponding to each of the periodicities that we suspect to be significant, we have to make that particular test, and therefore, the Bartlett's test is preferred for test of periodicities. Now, we will test for white noise or the assumption that we made that the series is uncorrelated, the residual series that we formulate is uncorrelated. So, in this we have the Whittle's test for white noise. Whittle's test, we formulate again the covariance matrix. Remember, we are dealing with the ET series, that is the residual series. So, the covariance R k at lag k of the error series ET is calculated. This is simply R k is equal to 1 by n minus k, j varies from k plus 1 to k, k goes from 0 to k max. K max can be typically 0.15 n here, E j into E j minus k. Then once you know the covariance, that is R k is given, you formulate the covariance matrix. So, covariance matrix will be of the size k max by k max. It is symmetrical R 0, R 1, R 2 etcetera R k max, like this you formulate tau n 1. This is a covariance matrix, and we denote it by tau n 1. Then we formulate a statistic. So, essentially we determined the covariance and formulated the covariance matrix. Using the covariance matrix, we define a statistic. Eta e is equal to n is given, n 1 is k max minus 1, rho naught is lag 0 correlation, which is 1, and rho 1 cap I will define now minus 1. Rho 1 cap here is determinant tau n 1 by determinant tau n 1 minus 1. Tau n 1 is given here. So, this is a matrix. The determinant of this is used here, determinant tau n 1. Now, tau n 1 minus 1 is constructed by eliminating the last row and the last column from the T n 1 tau n 1 matrix. That is, you have this matrix, you delete this row, I am sorry, the last row and the last column, you delete this row and this column. So, you will have tau n 1 minus 1 and the determinant of that is what is used here. So, you can formulate rho 1 cap. So, you know n here, n 1 is known, k max, rho naught is 1 and rho 1 cap is formed by rho 1 cap is calculated by taking the determinant tau n 1 is defined here, then take out the last row and last column, take the determinant and that is what defines determinant of tau n 1 minus 1. Therefore, rho 1 cap is known and therefore, you calculate this particular statistic. Once that statistic is known, this statistic is approximately distributed as f alpha n 1 n minus n 1, n 1 is your k max, typically taken as 15% of your n. So, as we did for earlier tests using the f distribution, you fix your confidence level typically 95% or 99%, n 1 is known, capital N is known, which is the number of values, and therefore, you know the critical value of f alpha. If the value of eta e that you calculate, this value, if the value that you calculate is less than f alpha, then the residual series is uncorrelated. So, this is what we do for white noise test. White noise is the series is uncorrelated. This is called as the Whittle's test. In fact, we have another test for examining whether the series E t is in fact white noise or not. It is called as the Portmanteau test. Now, this test is also carried out to test the absence of correlation in the series, and this also uses the RK as defined earlier, that is the covariance matrix as we have defined earlier. This covariance matrix is used. So, you know how to formulate the covariance matrix. From the covariance matrix, we start defining another statistic in the Portmanteau test. So, using the covariance matrix RK here, a statistic eta e is defined. N is the number of values, n 1 is your maximum lag and RK is corresponding to the covariance of order k, and then R naught is the covariance of order 0. So, k is equal to 1 to n 1. So, you know how to calculate the statistic value. Now, this statistic is approximately distributed as chi-square distribution with argument n 1. So, you fix the alpha and n 1 is your k max, which is the maximum lags up to which you have gone, and from the chi-square tables you can get this value. The value n 1 is chosen again as 0.15 n. So, get the chi-square alpha n 1 value from the tables. If your eta e that you have calculated is less than the critical value of alpha, then the residual series is uncorrelated. So, for the white noise test, that means to examine whether the series is uncorrelated or not, we have two tests, namely Whittle's test and the Portmanteau test. In both of them, we use the covariance matrix of the residual series and then formulate a statistic. Now, between these two, Kashyap and Rao have proved the same textbook that I have been mentioning. They have proved that the Portmanteau test is uniformly inferior to Whittle's test, and we prefer the latter for applications. So, while there are two tests that are mentioned, if you are in a fix which one to use, you always go for the Whittle's test as shown by Kashyap and Rao. Now, before we go to the applications, essentially what we have done is that we have formulated the models, ARIMA type of models, and then we have made the tests, and then we now start applying to different case studies. So, let us summarize what we did on the choice of the ARIMA models. This is not just what I have covered in this lecture, but also on the previous two lectures. We formulate the ARIMA models after differencing the series ARIMA, that is autoregressive integrated moving average models. the order of differencing, whether it is a first order or second order differencing, depends on the non-stationarity present in the data. So, you do the differencing essentially to convert the data into a stationary data. Once you have the data as a stationary time series, then you apply this ARIMA type of models. Now, in the ARIMA models, you know how to estimate the number of AR parameters and the number of MA parameters. In the event that you are not very clear about how many AR terms to use, how many MA terms to use, etc., you form the candidate models, a large number of candidate models, and then apply these candidate models to the observed time series, estimate the parameters and calibrate the models using part of the series. Typically, we use half the length of the data to calibrate the series and use these models for validation for the remaining part of the data. When you apply these models for the remaining part of the data, you get the residual series, that is ET series. We do the tests of validation on the residual series. We do essentially 3 different tests. One is to test whether the residual series has a 0 mean, or the mean of the residual series is not significantly different from 0. That is the first test that we do. Then we test whether the residual series that we have obtained by applying the model is devoid of any significant periodicities. So, you may come up with some periodicities, you test for the periodicities. We saw 2 tests for periodicity, for significance of periodicities, and we normally prefer the cumulative periodogram test for significance of periodicities. Then we also examine whether the series ET that we have obtained is in fact white noise or it is uncorrelated. For that again we had 2 tests, the portmanteau test and the Whittle's test. It is shown in the standard textbook Kashyap and Rao that the Whittle's test is better than the portmanteau test. So, we apply the models, make all these tests, and then make sure that the model that you have chosen, either based on the maximum likelihood criterion or the minimum mean square criterion, passes all these tests, and then choose that particular model for application. We will continue the discussion, and specifically we will see how to apply these models, whatever procedure that I have explained so far. We will see the applications of these in the coming lectures. Thank you for your attention.